says a student carries out the following tests on solid Q and make the observations recorded in the table. Complete the table to show possible inferences and write Ionic equations where required. So you are going to now look at this thing. Sorry. So a small amount of Q is heated in a dry test tube. A brown gas evolves which turns moist blue litmus red. Okay, so what could possibly cause moist blue litmus to be red and is a brown gas? That is the question. Here we go. Okay, so this paper that you're looking at is what I sent to you guys. Okay, this is the paper I sent to you, and I'm just gonna scroll down to the back of this paper. Here you go. So this is a table for gases. Once fumes are produced, it means a gas is produced. So let's see if we can find a gas which is brown. Here you go, brown gas. Here you go, red brown gas, bromine, choking, blue to red, then bleach, okay? Then you have nitrogen dioxide, red brown irritating gas, and it also changes blue litmus to red. So you might be thinking, now which one of these could this possibly be? Now it's almost never bromine. It's almost always nitrogen dioxide. So what you would do now in your table is write NO2 like that. Okay. It says another gas evolves which rekindles a glowing splint. So then now you can go back to your notes again, okay, and see which gas rekindles a glowing splint. Let's check oxygen. Look at oxygen. See there, it's a colorless, odorless gas. It has no effect on litmus, and it's see right there, relights or rekindles a glowing splint. So it means that our other substance over here, our other substance here. So you have NO2, and then this is oxygen. This is how you write your inference. You don't need to write it may be or it could be or anything like that. You just need to write down the things like that. Okay, so that's how you do that part. Then now let us see. We go down a little bit further now, right? It says a portion of Q is dissolved in approximately 10 mL of deionized water. The remaining solution is divided into 3 portions for tests 2 to 4. It says a portion of solution Q above aqueous sodium hydroxide is added dropwise until in excess. So sodium hydroxide, as I said, is used to test for cations. Okay, and then you add the excess. So it says here, when you add the sodium hydroxide, a white precipitate is formed. So I can now go back to my notes. Notice what I'm doing here. I'm toggling between the worksheet and the notes. So I go back around here now to my notes, and what I'm looking for is sodium hydroxide, test with sodium hydroxide. Okay, and we're almost there. See here? Cations. Sodium hydroxide and ammonia are used to test for cations. A small amount of solid is used to make a solution. Then solutions of sodium hydroxide are added dropwise. Test with cations. So when I add my sodium hydroxide dropwise, it says you get a white precipitate for calcium, white precipitate for aluminum, lead, and zinc. Okay, do you see that? So you see there that when you get a white precipitate with sodium hydroxide, see, white precipitate form. So it means that here I could have calcium, and you'd put the charge calcium, aluminum, lead, or zinc. All right, you see? Now it says here the precipitate is soluble in excess sodium hydroxide. So let me go back to the notes now and see which of these is soluble in excess. So I add the sodium hydroxide dropwise. I get a white precipitate for that, white precipitate there. For calcium in excess, literally the letters XS, which means extra or excess, the precipitate is insoluble for calcium. See, insoluble for calcium. But look here now, with excess aluminum, lead, or zinc, the precipitate is soluble. So let's go back to the table. That the precipitate is soluble in excess sodium hydroxide. Okay, so up here we would have aluminum, zinc, lead, calcium, but down here now we would have aluminum, zinc, and lead, because those are the only ones which produce a soluble precipitate in excess. Okay, so let us proceed again further. It says, you know, to another portion of Q, aqueous ammonia is added. Ammonia is used to test for or to confirm the presence of certain cations. So we go back to the table. Let's see what our table is saying to us around here. So that is test with sodium hydroxide. We scroll down a little bit. And now when we go down, it says test with ammonia. So when we add the ammonia dropwise, we get no precipitate if it's calcium. No precipitate is formed. We get a white precipitate. If it's lead or aluminum, we also get a white precipitate if it is zinc. So let us go back to the table again to see what we actually got. So it says when we add ammonia, what we get a white precipitate. There you go. So we get a white precipitate, which means that it could possibly be lead, aluminum, or zinc. You see that? Okay, so we possibly could get any of those things right there. No, it says the precipitate is insoluble in excess ammonia. It is insoluble in excess ammonia. So let us check which one of these things would be insoluble in excess ammonia. All right, so we go back again to the table. Notice I'm toggling between the table and this. All right, so we get a white precipitate for aluminum and lead, but look at that. The precipitate for aluminum and lead is insoluble. Okay, so it now means that we can eliminate zinc because zinc would be soluble. So I'll write those again. So up here we had aluminum, lead, calcium, zinc. Then we eliminated the calcium. Aluminum, we got lead here and zinc here. Then down here now, we got aluminum, lead, and zinc. And these are ions. I'm not writing the charge because of the space, but you should write the charge for sure. Okay, and then now we eliminated the zinc, and down here we have aluminum and lead. So in your qualitative analysis now, this is the thing. You got a solid. You heated the solid, right? Brown gas was produced, and another gas which was produced that relights a glowing splint. Okay, then when you checked for cations, you found that a white precipitate was formed, and that suggested that it could possibly be aluminum, lead, calcium, or zinc ions present. But then when you added excess sodium hydroxide, you found that it was soluble, which could only mean aluminum, lead, and zinc. Now, you want to confirm or really reassert what you have from the sodium hydroxide test. So you go further now and you do your ammonia test. With your ammonia test, you got a white precipitate. The white precipitate suggests that aluminum, lead, or zinc may be present. Then now, when you added excess ammonia, it is insoluble, which means that it could only be aluminum and lead. So now what you're faced with is this. You now have two cations and you need to distinguish them. You need to determine which of these cations is present. So how do we do that? The good thing is this. There is a specific test to determine if lead is present. All right, so you have two things now, aluminum and lead. If you can say lead is present, it means that it's not aluminum, clearly. Okay, so now what do they do? Down here, to another portion of Q from above, aqueous potassium iodide is added. A yellow precipitate is formed. Now, I can categorically tell you this right now. Once you add potassium iodide to our solution and a yellow precipitate is formed, it means that lead ions are present. Every time you do qualitative, that is the case. Okay, so you now need to write an ionic equation for this. Previously, I said to you guys, you need to practice those ionic equations because you're going to be able to use them all the time, just like that, without even having to think about it. So I'll write the equation for you. And the equation is always the same for the formation of this yellow precipitate. So what we have is We have lead because the yellow precipitate means lead is present, plus 2I, and all of these are aqueous. I'm not putting the states because of the space. Produce PbI2, and I'll put it for this solid. This is a solid because it's a precipitate. Lead is present, and you want to confirm or deny if it's present, you use lead iodide. Okay? So it's going to be the ionic equation you're using always for this reaction. I would say, to be honest, you shouldn't memorize it. You should know how to write it. But if you have to memorize it, you have to memorize it. Remember, I didn't put the state symbols for these two things, but they are aqueous. All right? And this is, of course, a solid. If you don't have the state symbols, you're going to lose 1 mark. Just saying. All right, so that's that. If you have any questions, oh, sorry. It then says down here, let me clear all drawings. Wait, let me not clear all drawings. It says down here now, suggest the possible identity of Q. All right, so every compound that you're given is going to have a cation and an anion. It's going to have something which is positive and it's going to have something which is negative. We have just identified the cation. It is obvious to us that the cation is lead. So it's a lead-based compound. Okay, now we need to find out what the anion is. Now, if you look in this table, you realize that there was only one anion test. Everything down this section, where's the spotlight? Everything down here has to do with cations. Everything here. So the only thing in this really that tells you about an anion is up here. Now, a brown gas was formed, and we have identified that brown gas. We have identified that brown gas as NO2. Now, there's only one place NO2 can come from, and I said this the last time. The only anion that can produce NO2 is NO3 minus the nitrate ion at this level. Okay, so therefore, our anion is going to be nitrate. Therefore, the identity of our compound is going to be lead nitrate. Okay, lead nitrate. There you go. Cation, and this is your anion right here. That's your anion. So your cation is lead, your anion is nitrate. All right, so you almost never have to read up here because they're going to say the same things, pretty much. The letters might change, but that's not really all that relevant. So let's see what happens, you know. It says, to a sample of solution P, dilute nitric acid is added, followed by a few drops of silver nitrate. Now, you may be asking yourself the question, what am I testing for if I add nitric acid and silver nitrate? Nitric acid is a very, I would say, broad brush solution because it's an acid, so you can use it to test for a lot of things. Okay, the big thing here, though, is silver nitrate. Silver nitrate, what on earth does silver nitrate test for? So I'm going to go back to the note. Let's see if we're looking for silver nitrate. Look at this. Here you go. Silver nitrate. The presence of halides, that is group 7 ions, can be confirmed with silver nitrate followed by ammonia. A solution of the solid is made and a few drops of silver nitrate are added, followed by a few drops of ammonia. So even though the acid was added, the acid was just there to dissolve any solid present. Okay, and then the important part is the silver nitrate. So I'm just going to keep this table right here, and we're going to go back to the table and see what we have here. So they have no observations, but what they say is that there is no chloride, no bromide, no iodide. Now, if you add silver nitrate and a halide, bromide, chloride, or iodide is present, then you must observe something. So let's see what you would observe. It says, well, not confirmatory test, but so you have the effect of silver nitrate. See it right here, effect of silver nitrate. So you get a white precipitate. I'll undo that. See, you get a white precipitate there. Remember, precipitate is a solid. Then you get a cream precipitate. Then you can get a pale yellow precipitate. So what does this mean? It means that once you're testing for a halide with silver nitrate and a halide is present, you must get a precipitate. See that? All of them produce a precipitate. So, but what does it say in the table? In the table, it says that no halide is present, which means that in my observation, I would have no precipitate. Because if a halide was present, I would get a precipitate. I would see a solid forming, whether it be white, cream, or yellow, but I would see something forming. Since I got no precipitate, it means no, since I got in the inference no halide present, then the observation would be no precipitate. Solution of, to the sample of solution P, a few drops of copper turnings is added, followed by sulfuric acid. Now you are thinking to yourself, I've never seen this one before. What does copper turnings and conc sulfuric acid test? And notice I said conc sulfuric acid and not concentrated, because we don't usually say concentrated in chemistry. As a shortening, we just say conc. All right. So conc sulfuric acid. So what does conc sulfuric acid and copper turnings test for? Well, before I get there, let's just look at this. It says brown fumes evolve. And notice you saw that before, brown fumes. What is this brown fumes again, which turns blue litmus red? As I said, when we saw in the table, bromine was an option and nitrogen dioxide was the other option. And I said categorically that it is almost never bromine, which means that it is nitrogen dioxide. Okay? So this must be nitrogen dioxide. But let us go to the table now to see where I got this information from. We can highlight it. I'm sure you can see this. Where's my thing? See it right here. Test sulfuric acid. Sulfuric acid. See? Conc, this square brackets with the H2SO4 in there means concentrated sulfuric acid. So that's how it's read. Concentrated sulfuric acid and copper turnings, which you saw in the table, are added to a solid and warmed. What are the observations? Blue solution forms and nitrogen dioxide is formed. NO2 is formed. If NO2 is formed, what would we observe? If NO2 is formed. So let's go back down to the table. You see, this is how you have to use the notes, you know. Any observation you have, it's there. NO2. See? Red, brown, irritating gas turns blue litmus red. So we know for sure that it is nitrogen dioxide that is formed based on all of that. So let us go back again to the board. All right. So I actually eliminated that bit, but this is supposed to be NO2. Right? So we have actually identified our anion already. Remember, every qualitative, you're trying to identify a cation and anion. So you basically have identified your anion simply by getting this. Okay, so we proceed. It says now to a sample of P, a few drops of acidified potassium manganate solution are added. The potassium manganate solution changes from purple to colorless. Now, why on earth would this change from purple to colorless? And what is potassium permanganate or potassium manganate 7? Sorry, it is the same thing as potassium permanganate, which is a purple substance. Okay, now if you come around to this table, this last table that I have in the notes, and you can actually look for the potassium permanganate and see what gas or which substance it's used to test for. See it right here? But turns acidified potassium permanganate, you have to know how to read these things, from purple to colorless. Was the solution changed from purple to colorless? Yes. All right. Let's see if there's another one. No other one. However, this substance here, nitrogen dioxide, can actually change it from purple to colorless as well, because it is an oxidizing gas. So it can, reducing gas. So it could actually do that as well. So what do you write for your inference there now? That is, I'm sure, the big question you're asking yourself. So what you could do is write reductant present. Because there could be so many reductants. Jesus. Reductant present. All right. There are a number of reductants. And you could put NO2 as well. All right, because we know NO2 is present from the brown gas above. Then now let us proceed. So now look at this. It says to a sample of solution P, aqueous sodium hydroxide is added onto the next. In this case, we get a green precipitate. So let's see if the notes have, even though this says dirty green and the thing said green, it's green. Isn't that the fundamental thing? Whether it's dirty or clean, it's green. So watch this now. It's iron 2. Dirty green means iron 2. Now look at what happens with the precipitate. The precipitate is insoluble in excess sodium hydroxide. I didn't read that part yet. So let us go back and see if it was insoluble indeed. There you go. The precipitate is insoluble. See it right there? The precipitate is insoluble. So this means that up here we can write Fe2 plus, and then down here we write Fe2 plus confirmed. Okay? Because the results are telling us, first of all, from the green precipitate, that iron 2 is present, and from the precipitate being insoluble, that Fe2 plus is definitely there. Okay? So we proceed. Let's see if there's anything else to answer. Wait, they asked for an ionic equation here. They asked for an ionic equation with sodium hydroxide. Now, every time you write an ionic equation with sodium hydroxide and a metal, it's always going to be like this. I'll write it generally first. It's going to be metal N plus, and M stands for metal and N is the charge of the metal. That's all. Okay, and you're going to see that. Plus your NaOH, same NaOH, to produce MOHN. All right. So we have Fe2 plus, there's the charge, plus 2OH, because the charge of iron there is 2. And of course, these are aqueous. Let me put the aqueous. You may not see them, but of course, they're aqueous to produce Fe, open bracket, OH2. There you go. And this is a solid. That's your ionic equation. Well, just came up with that. So that's your ionic equation for that reaction. And notice here now, behind this thing, I hope you can see it. Your ionic equation is worth 2 marks. See, I'm circling it right there. It's worth 2 marks. So you need to make sure you do it properly. Okay. So it says to solid Q, water is added, it stirred the filtrate 4 portions, etc. Notice I'm not even reading that. Basically, I'm telling you, you really don't need to read that into that much. So the first portion of the filtrate from above, sodium hydroxide, is added until in excess. Sodium hydroxide is used to test for cations. Notice here, they didn't give us observations. What did they give us? An inference. They said aluminum, lead, zinc, and calcium is present. We can write here white PPT, and you'd write white PPT formed. Of course, this is just on a board. Then now, you remember, it says now when we add excess. So I want you to recognize that there's a dot here, there's a dot here. You see, there are 2 dots. You have 2 dots because one is for when you just add the sodium hydroxide and one is for the excess. So when you add the sodium hydroxide first, you get a white precipitate. Then when you add excess, it says aluminum, lead, and zinc is present, which would mean that the precipitate was soluble. So that's all you need to write. PPT soluble. Okay, that's great. Now we proceed to the second portion of the filtrate. Ammonia is added until in excess again. Now it still says again that a white precipitate is formed. And if you remember, with the white precipitate with ammonia, I can toggle back to the book, but the handout, but you can read that for yourself. If it is a white precipitate, then these 3 are the guilty suspects. So I'll just bring them down like that, right there. Okay, bring them down like that. Then now it says the precipitate is soluble in excess aqueous ammonia. So if the precipitate is soluble, it now eliminates zinc. So down here we have lead and aluminum. All right, see? So notice we started out with 4 cations. We eliminated 1, then we go to 3, and then we were confirming 3, and now we're down to 2. So now remember again, I said this should look familiar because we just did it, that you need to know the cipher between the lead and the aluminum. So look at what they did. They added aqueous potassium iodide. Yellow precipitate formed. Yellow precipitate will always be the same thing. You should be very excited when you see that because you know exactly what it is. That's lead iodide. So now you need to write the ionic equation. Pb2 plus, aqueous of course, plus 2i, undo that, undo. 2i to produce PbI2 solid. And that's your ionic equation, which is worth 2 marks. Do not play with that. Okay? And I just showed you how to do the general equation for it. It says to the third portion from above, to the fourth portion from above, silver nitrate is added, followed by aqueous ammonia. And we just did this too, didn't we? Silver nitrate is used to test for halide. And it says no observable change. So if there's no observable change, it means that no halide is present. No halide is present. All right? So that's no halide. This is hard. No halide. All right. Then no, it says, so we still proceed again. Okay. It might seem like it's not connected sometimes, and you're like, am I not trying to identify one substance? Sometimes they have a mixture of substances. So you might be getting results and you say, but hold on, I've confirmed and I know for sure that this is present. So why is it I'm still seeing another anion here? That's because they mix the sample. All right. So they may put in 2 cations and 2 anions in there and say you need to identify what they are. All right, so we proceed. Now it says to the dry residue from above, add nitric acid, filter, and then divide the filtrate into 2 portions. Notice we have added nitric acid. It says when you add nitric acid, vigorous effervescence upon addition of nitric acid. Now an acid, and you did this in 4th form, acids react with certain substances, of course, to produce a gas. Acids react with metals to produce a gas. You are not doing that in qualitative analysis, so forget that one. Acids react with carbonates to produce salt, water, and carbon dioxide. Also, acids react with sulfites to produce salt, water, and sulfur dioxide. You remember last week I showed you how to decipher between sulfur dioxide and carbon dioxide. Sulfur dioxide is a colorless gas with a choking odor, and it will turn blue litmus red. Yes, carbon dioxide is a colorless, odorless gas, right? And it will change lime water cloudy, okay? And of course, it will also change damp blue litmus red. But the crux of the thing is that sulfur dioxide is a gas which has a choking odor, and carbon dioxide produces white substance when it is in litmus. So here we go now. Vigorous effervescence of herbs observed upon the addition of nitric acid. So what could possibly be present there? If you have effervescence, you could have carbonate or you could have a sulfite. But then no, sulfite, SO2, SO3, 2 minus. But then no, down here, notice it says gas evolved, and let me point to it. Gas evolves, which turns lime water cloudy. What would turn lime water cloudy? Carbon dioxide. Where do we get carbon dioxide from? The carbonate ion. There's no other place for you that it is going to come from. Okay, so now you need to write an ionic equation again. Ionic equations are all here. So I cleared it to get space for the ionic equation. So since it's carbon dioxide, which is turning lime water is actually calcium hydroxide. So it's reacting with a base. And this produces, I'm going to bend it a little bit. This produces calcium carbonate, which is a solid, plus water. So the white substance that you see that makes the lime water cloudy is actually calcium carbonate. That's what makes it cloudy right there. Okay, and this is your ionic equation. Of course, carbon dioxide is a gas. This is aqueous. This is a solid, not a L. It's not a liquid, it's solid. And of course, water is a liquid. All right, so that's your ionic equation. And every single time that carbon dioxide is produced and the ionic equation is required, this is the ionic equation that's required. Okay, so we proceed. It says to the first portion of the filtrate from above, add sodium hydroxide until in excess. Remember, sodium hydroxide is used to test for cations. Here we go. Copper 2+ ions present. What would we observe if copper 2+ ions are present? So let me go back to the document so you can clearly see that. So here's copper. When you add dropwise, you get a blue precipitate. Then now, in excess, the precipitate is insoluble. All right. So we know what we should be seeing here. Okay. So since we have copper 2+ ions present, then we would see over here a blue PPT. Notice PPT is acceptable. Then now, when you add excess now, PPT insoluble, PPT insol for short. Now over here, you need to write an ionic equation. Remember, I just showed you how to get the equation for any reaction with sodium hydroxide for the metal. So it's Cu2 plus 2OH to produce CuOH2. And of course, this is a solid. And this is aqueous, and this is aqueous. So that's your ionic equation. All right. Now, the second portion of the filtrate from above, ammonia, is added. Since copper ions are present, let's see what would happen with copper ions in ammonia. It might be a little bit different. Ions with ammonia. With dropwise, if it is copper, what do we get? Blue precipitate. When it goes to excess, you get a precipitate soluble, gives deep blue solution. So you see it's a little bit different. All right, so let us go back to the table now. So for over here, when we add the ammonia dropwise, what do we get? Blue PPT, blue PPT. All right, and then when it is in excess now, you get PPT soluble blue solution or deep blue solution formed. All right, so that's what you would write. Of course, I'm writing on a screen, so the space is not going to fit it. All right, so that is that bit. Okay. All right, so let us proceed. So again, you don't need to read the top bit there. That's, yeah. So let us look at this bit now. To a sample of solution X, dilute nitric acid is added, followed by a few drops of silver nitrate. What is so now? It says when you add it, a white precipitate which turns gray-black in light is silver nitrate. You get a white precipitate. Which cation is that? Chloride ion. Okay. And then now, what is this now? Reason silver chloride formed. Effect of ammonia, precipitate soluble. For this, we would write Cl. And then now they ask you for an ionic equation. Of course, since silver chloride is formed, right, you just write AgCl over here. And it's a solid, of course, since it's a precipitate. Silver chloride can only come from silver and chlorine. There is nothing else it can come from. So silver has a +1 charge and chlorine has a -1 charge. And of course, these two things are aqueous. So that would be your ionic equation right there. Okay, let's go to the next question. It says to a sample of solution X, aqueous sodium hydroxide is added until in excess. Sodium hydroxide, cations, just try to remember. Okay, a pale blue gelatinous precipitate is formed, which is insoluble in excess. Therefore, what we have now is Cu, 2+. And of course, this is chloride, this is Ag+, and this is gonna go away. Why am I writing it back? Okay, and then now we move down a little bit on the paper. Let me clear all. Sample of X, acidified potassium manganate is added, and the solution is heated. The potassium solution is decolorized. The potassium manganate solution is decolorized. As I showed you earlier, this could happen because you have NO2 present, NO2, or SO2 present. Okay, so you could write both of those and you'll be fine. Then now it says we proceed again. Do that. Right, we proceed again, clear that. So a solution of sample of solution X, barium chloride is added. Now, this is the first time you're seeing this one, barium chloride. So let us go. What is barium chloride used to test for? Let's go to the note. So the presence of sulfite, carbonate, let me use this highlighter. Sulfite, carbonate, hydrogen carbonate, and sulfate can also be confirmed. Make a solution of the solid, and to this add a few drops of barium nitrate or barium chloride. It doesn't matter which one, followed by a few drops of dilute acid. So what do we get? When we add the barium chloride, we get white precipitate, white precipitate, white precipitate. For all of them, it doesn't matter which one of the anions, whichever one of these, it doesn't matter. It is, you're going to get a white precipitate. Now, notice here now the effect of acid. The precipitate is insoluble in the acid for the sulfate ion. See, it is insoluble for the sulfate ion. And that's the reason over there. Barium sulfate form, but it does not react with acid. White precipitate again. Precipitate soluble, carbon dioxide form. That means that you have a carbonate, hydrogen carbonate. Barium carbonate formed and reacts with acid to form carbon dioxide. Then now look at this over here. You have a white precipitate. Precipitate soluble in the acid, Sulfur dioxide formed. Sulfite ion is present. Barium sulfide formed and reacts with acid to form sulfur dioxide. So let us go back now. You see, all of those notes can guide you into what you should write as your answer. So you see, we get our white precipitate. So what could be present? What could be present could be carbonate, sulfate, or sulfite, SO3 2-. Now it says the precipitate dissolve. If the precipitate dissolves, we know it is possibly going to be the carbonate or the sulfite ion. I will write the correct formula, but say the incorrect name. Okay, so those are the things that would be present. So let's do this last one. A sample of solid Y is moistened with sodium hydroxide. Sodium hydroxide used to test for cations. Moist red and moist blue litmus are held at the mouth of the tube or the top of the test tube. A pungent gas evolves and it turns red litmus blue. Which gas is pungent? Let's go to them. We're looking for pungent. Pungent is a scientific word for stink. In science, we don't say stink, we say pungent. So we're looking for the word pungent. Oh, wait, there it is right there, pungent. Voila. Pungent, it's actually the only gas which is pungent, and it is ammonia. That urine smell is ammonia, coming from ammonia. So if ammonia is the only common alkaline gas, it is the only common gas that is going to change red litmus to blue. See it right there? Red litmus. Effect on moist litmus, red to blue. If you look through the line, it is the only one that actually changes red litmus to blue. Okay, so we know for sure that it is ammonia. Now, ammonia, if you recall, I said like carbon dioxide can only come from carbonate. Nitrogen dioxide can only come from nitrate. Sulfur dioxide can only come from the sulfite ion. Well, ammonia can only come from the ammonium ion. All right. So this would be NH3. Now you don't need to write suspected. Then down here, when it changes it now, you say NH3 confirmed, because that's a confirmation for that. All right. Then now let's look at this now. To a solution, a few drops of acidified silver nitrate. What is silver nitrate test for again? Halides. Okay, so a white precipitate is formed. White precipitate would be chloride ion. And see, they ask you for an ionic equation again. You can, of course, check the notes for that. And of course, you write your ionic equation, Ag, to produce AgCl, which is a solid, of course, since it's a precipitate. And silver has a +1 charge. Okay, the precipitate dissolves in aqueous ammonia, and this is just confirmation that it is chloride ion. Remember, just go to the notes in the thing and you will see it clearly. All right, now to a solution, aqueous solution of double, a solution containing barium ions. Barium ions. There was only one place barium ions were mentioned, and I just showed you. Barium ions are used to test for sulfate, sulfite, and carbonates. So if any of those are present, you get a white precipitate. So when they added the barium ions, they got a white precipitate, which means that carbonate, sulfite, 2-, and sulfate is possibly present. Any one of those is possibly present. Okay, now let's see the last bit of testing. The last bit of testing, and I'll clear the drawing so you can see. It says dilute hydrochloric acid is added to the mixture from above in 3. So this one with the barium ions. It says the precipitate is insoluble in acid. Now for this one, I'm just going to go back to the notes just to show you that bit, acids, just to show you that one. Okay, here you go. See, barium ions, white precipitate, white PPT, white PPT. Effect of acid, precipitate insoluble. Which ion is present? The sulfate ion. Okay, that's how you have to read the table. So when we go back around here now, it says you need to write an ionic equation. Now, let me go back to the notes. In the notes, it says barium sulfate right there is formed. Now, what would form barium sulfate? The only two things can form barium sulfate, and that is barium, which has a 2+ charge, and the sulfate ion, 2-, to give you barium sulfate. Okay? And that's the end of the story right there. See, there you go.